Hi, my name is Shan Yi, and together with my group mates, Cui Nan, Pu Fanyi, Zhang Kaichen, and Tian Yidong, we will be presenting our project on the design and implementation of the storage and indexing components of a database management system. Our content will consist of three main parts, including the design of the storage component, index components, and the implementation and experiments.
In this section, we illustrate the design of our storage components. We begin by listing all the components in our design, followed by a demonstration of how each component interacts with the others. The data components primarily consist of the following objects: a block data, the object that stores actual data; a block pointer, this object points to the position of the block data; a data pointer, this object points to a specific range of position within the block data; a recall is a subclass of the data pointer. It can access a specific range within the block data, but corresponding to the size of the recall. A schema. The schema manages the field and names and data types of the table. During the reading and writing processes, all data is converted in a uniform format of an array of bytes. During reading, we only access the block pointer or the recall pointer, which points to a specific location in the data. When that specific range is needed, the corresponding byte array is loaded into memory. Then we will illustrate our controller components, which are primarily have two objects: a file manager. This object manages all the block pointer instances in the file stream. A database manager. This object controls the database. We use file manager to load data or allocate new memory for data storage. When interacting with the reader, database manager calls the file manager to allocate new memory or read from existing memory. And during a load operation, the database manager initiates an I/O operation for one block. Then we'll introduce our buffer pool design. We use the buffer pool to manage disk read and write operations uniformly. All database read and write operation must go through the buffer pool. The buffer pool has the following properties: a hash table. It uses the disk offset as a key, represents the block data corresponding to the disk offset. A least recent use queue that tracks the access order of frames, with the LRU page at the head. This queue implements the page replacement policy in the buffer pool. A dirty bit. Each frame in the buffer pool is associated with a dirty bit D. If the D is equal to 1, the frame has been modified in memory, but not yet written back to disk. If D is 0, the frame is synchronized with the corresponding block on disk. And during actual I/O operations, file manager manages the buffer and reuses it if the buffer is already cached. If the buffer pool is full, it is updating using the LRU policy described above. The structure of our buffer pool is illustrated in the figure shown, where each block data is shared using a share pointer or a weak pointer to allow resource sharing. And during updates, the data in the buffer is modified accordingly, and the pointers are updated to reflect the changes. The entire structure simulates the LRU process, achieving a constant time complexity for each fetch operation.
To perform a large number of query operations, we maintain an index by constructing a B+ tree. To minimize corner cases, we refer to the simplification of B trees as described in the introduction to algorithms. We use T, the minimum degree of each node, as a constraint for the entire tree. The maximum number of indices each node can be stored, donated as n, can be calculated as 2t minus 1. It is straightforward to see that the maximum degree of each node is 2t. In this way, n must be an odd number, which eliminates the need for extensive rounding operations. We use bulk loading to quickly build the B+ tree. First, we sort all the indices in O log n time. Then, we construct a row of leaf nodes. Each node is assigned t indices, while the last leaf node can hold up to 2t indices. It can be proven that only the last node needs to be considered in this scenario. After constructing the leaf nodes, we use a function called bulk loading upper layer to build all the upper level nodes. Similarly, we try to place only t nodes in each internal node, so that only the last node requires special consideration. After completing this layer, we continue to recursively build upward until there is only one node in a layer. This node becomes the root node of the B+ tree. Next is the algorithm for range queries. The range query function takes the following parameters. O represents the current node. L and R represents the query range. The big R is a result sheet, which in C++ is a pointer to a vector. We update the result by continuously update big R. We categorize the nodes based on whether they are leaf nodes. In a node is not a leaf, we search for the first record that meets the condition. We can perform a binary search on the trial nodes and then recursively search through that node. If we find a child node, it means that we have located the leftmost records that satisfy the condition. At this point, we continue to recursively search the right until we exceed the upper boundary.
Then I will move on to the 3 tasks. In our database system and in the provided file, a record consists of an array of 45 bytes. Since there are 26,651 lines in the file, there will be the same number of records in the database. Our block size is set to the default value of 4096 bytes. Therefore, each block can store 91 records. To store all the records in our database, we will need 293 blocks. A database file in our system is a binary file. It contains multiple blocks used to store the database data. This table shows the result of task 1. In our B+ tree structure, degree T is the minimum number of subtrees of an internal node. In our B+ tree, the degree is 102. The parameter n is restricted to be an odd integer, which refers to the maximum number of keys that can be stored in a node, so n equals to 203. Since each leaf node must store at least 102 keys, there will be 262 leaf nodes. Each internal node can have at least 102 pointers. Therefore, the number of internal nodes at the first level is 3. Since there are only 3 internal nodes in the first level, the second level will contain 1 root node. Therefore, totally there are 263 nodes, and the B+ tree has 3 levels. The root node will contain the first key from each of its 3 children. Since there are only 3 internal nodes, the root will contain 3 keys that guide the search process to the appropriate internal node. This table shows the result of task 2. We will now present the statistics required for task 3. The results were obtained by running the system with different buffer sizes, and the outcomes are summarized in the table. Without using a buffer, the number of I/O operations for accessing index blocks is 66. When using the buffer, as the buffer size increases, the number of I/O operations for accessing the index decreases gradually, as portions of the index are stored in the buffer during the building phases. Since we use a dense, non-clustered index, many data blocks are accessed multiple times because the records are not stored sequentially. The high I/O in data block access results in the runtime of the B+ tree being longer than that of the range query. This issue can be mitigated by increasing the buffer size, as the linear scan cannot fully utilize the buffer, and the B+ tree will have a shorter runtime with an increased buffer size. The average FG3 PCT home value retrieved from the return record is 0.420801. We verified this result using a simple Python program which returned a value of 0.420815. Thus, we confirm that the query result is accurate. The algorithm's running time without using a buffer is approximately 39 milliseconds. When using a buffer, as the buffer size increases, the running time decreases to around 9 milliseconds. Detailed statistics can be found in the table. The number of data blocks accessed by a brute force linear scan is constant at 293. The running time for a linear scan is constant, taking approximately 22 milliseconds. A detailed comparison can be found in the figure. The figure A shows the comparison between different buffer size and data block access for B+ tree. Figure B shows the comparison between different buffer size and index block access for B+ tree. The figure C shows the comparison between different buffer size and runtime for B+ tree and linear scan.
Enter your build directory, do cmake, and then make. To get most of the test result, we can run unit test. This will build and run most of the test result. As you can see, the I/O times for linear scan will be 293, which correspond to our block size, our block number. And here will be the scan time for our linear scan. We can double confirm that our block size is correct by checking the number of bytes. As we can see, this number is just equals to 293 times 4096. We can also double confirm at here. You can see that the total record size is equal to this value, and the number of record size that returned from the query is equal to this value. To get the result from the range query using B+ tree, you can run project 1, and it will show the number of nodes and the number of records and the number of T. The I/Os are almost 0 here because we are using a large cache value by default, and it will cache most of the result. And here are the query time. To double confirm the block size is correct, we can also use this command, which shows that our result is compatible with our system.
Thank you. That's the end of our presentation.